So, moin! This video is part of the scientific Python programming lecture at the University of Bremen, and in this session we would like to learn something about testing, code testing and code testing coverage. And basically that's a very important session. We will not learn new Python commands basically or new Python constructs. We will concentrate only on the question, how can I ensure that my code behaves as it is supposed? And if I make a mistake during the development, so I introduce a bug, how I can very efficiently find that bug. And this is exactly why testing is so very important, because all of us would like to spend time on developing new cool features in our programs and maybe spend less time in finding annoying bugs, which can be sometimes very difficult to find. And basically a good automatic testing and a good test coverage can help us to reduce the time which we spend on looking for bugs and errors, and basically increase the time which we can spend on developing new cool features. As always, we will do everything in our Ubuntu virtual machine. Basically, as always, you can find the code at the usual address at the website of the course. And basically we will need, in order to cover the topics, we will need to install a few packages which you already know how to install yourself, so I won't guide you that. Please make sure that you install those packages because we will use them in the sessions. We will talk in this video basically about the program testing and the testing coverage, and in the following session we will talk about code analysis. If you are talking about testing, then basically we are setting up a framework which can ensure that our programs are working as supposed, so basically working correctly. And in the code quality analysis, that's a second part. In the next video, we will just make sure that our code is not just working correctly, but it's also readable, so it's written nicely. And this is also something, those two aspects are incredibly important if you are developing, and basically they are basically the two most important things. Your code is tested well, so you can be sure it's working correctly, and people can read it because it's written nicely, and people can also contribute to that because it's written nicely. So let's start with program testing first. And just here you can see a scenario which can happen during code development, of course, is that you are writing, why do we need testing at all? You are writing here a program, and then of course when you write a program and you add a feature like we had with the solving a linear system of equations, then you try it for a few examples and you see you think it's working, then you are basically satisfied and say, okay, the feature had been implemented, so let's move to a new feature. But of course, when you're changing your code again and again, then the question is always, how do I know that the old tests are still, the old cases, the old features are still working correctly? Sometimes I'm just only refactoring the code, which means just restructuring it without changing the functionality. How can I know that basically that what have worked before is still working? And that I cannot decide unless I'm making tests which are ensuring that. The second purpose of tests, so that was basically saying, okay, it works on my machine correctly. The second motivation for having tests is if I'm just giving my program away, and usually programming is something about sharing, so basically usually you are not writing the programs only just for yourself, but you try to share it in a community so that other people can also profit from your efforts. Then how do you know, or how do people know who are downloading your code, that the code works on their machine as it's supposed to be? And of course you could think, okay, it's Python, so if Python works in a Python program works in a certain way on my machine, it will work exactly the same way on a different machine. But it's not necessarily true, especially if we are talking about using scientific libraries, numerical libraries. The implementation of the numerical library of somebody else's machine could be different, a different version, or even a completely different implementation. And then I have somehow to make sure that the program works in that environment where they are supposed to use it, that it works the same way as on my environment. And that's the second reason to have tests. You can just deliver that test with your program. Then the consumer will just run those tests on his machine or her machine with your program, and basically if the results are the same as on your machine, so that all the tests are passing, then there is a good chance that the program works on that environment exactly the same way as in yours. So those are the two very important motivations for making tests. No, basically you can ask the questions, when should we test, right? And basically, of course, as often as possible. And it's very, very important that when you change the code, it should be tested after each relevant change. So basically, if you just let's say fixing a typo in a comment, then maybe your code didn't change. So it's not necessarily to test, but whenever you change code lines, you should make sure that you are testing your code. And as I said before, whenever you are going to a different environment, so the code is distributed, it should be tested. And that means it needs a lot of testing. And testing you will only do if it's easy to do, right? I mean, if you have to do something very often, but that what you have to do is complicated, there's a high barrier, it's complicated to execute or takes too long, and that means you will not do it at the end. And therefore, it's very, very important that we have an automatic test framework which we just have to set up once, and then whenever we want to have a test, we just have to execute one command or push a button in our development environment, and then the tests are automatically executed, so that basically testing should be part of our workflow. And especially if you are later collaborating with others on platforms like GitHub or GitLab, so basically on public platforms, you can even make a so-called continuous integration framework where whenever you check in something, automatically tests are run. But it's also very important that you can run tests on your machine during development to make sure, even before checking in things, that your code works correctly. And this is exactly the part or the topic of this video. We would like to set up a test framework which you can use to test our codes. Just before we do that, maybe just two things to add in the what kind of testing you can think about. And there are basically two different group of tests. Let's say the so-called unit test or white box testing, and that's an approach where you are basically taking every routine, and for every routine you write a test. So that means basically whenever you code up a routine which does something, first or after that, depending, you're writing a test which is testing that. That means you have to write quite a lot of tests, but the nice thing is your tests are very granular. That means that basically whenever you have a bug, you immediately know in which routine, in which function basically this bug occurs, or which function is responsible for the bug. The other big type of tests are the so-called regression tests, and that's a little bit, or we can call it black box testing, and that means you are basically just giving the input which the user, the consumer of your code, would give to your program, and then you are checking that for a given input, a given output comes out. So basically you are not dealing with the internal details. If you are refactoring things, you don't have to change your tests, because the tests are only dealing with the input and the output, and doesn't deal with the internal structure. The nice thing with that model is that if you are reordering your code, your tests are still the same, they don't change. On the other hand, if you find a mistake, a bug somewhere, then it's more complicated, or find the bug, it's more complicated to find where it is, because you don't have a granular test of all the functions separately. Very important is that you always write tests, and actually in agile programming, one of the paradigms is, and I think it's a very, very nice one, that you are writing the tests first. So basically whenever you say, I want to implement this and this feature, the question you should ask yourself first, how will I test it? And if you know how will you test it, you should write the test immediately, even before implementing the feature. So basically you are writing the test, and you exactly know that you will be able to test the functionality of this feature. Then you can start implement the feature, and basically when you implement the feature, you have to change it as long as the tests are passed. Also, sometimes if you are finding a bug, that basically means that your testing system was not good enough, because there was a case where you could make an error in the code without recognizing it. That sometimes still happens. So the first thing what you could do is to write a test for that, even before fixing the bug. So you can write a test for that feature to make sure that the bug occurs and the test fails during the test. And then basically you fix the bug, and you see you can have a look whether basically the fixed bug is with the bug fixed, whether the tests now passes or not. So basically what you have to do is whenever you find a bug, that means there was a path of your code which was not tested correctly, maybe with some combination of input values. So first make sure that you make a test for that and then fix the bug. And with that, gradually, basically, you can achieve a very solid and robust test set, which makes sure that your code works correctly. And if you just break one feature, that you will get notified about that. There are various ways how you can achieve that in Python, various automatic testing frameworks. There is one which is shipped with Python itself, the unit test package or unit test 2 package, depending. And this is something which the nice thing with that it comes in Python automatically. It needs a little bit more programming than what we will do. It's object-oriented. If you know object-oriented programming, already have a look at that, and it's a very powerful package. What we will use is the so-called PyTest package, which is a third-party package, so it's an extra dependency, but basically you find it in any kind of distribution, Linux distribution, without any problems. And the nice thing with PyTest is that you can make things much easier in a few lines, basically, what is sometimes more complicated with unit test. The only thing is, if people are using your package, they would have to make sure that they also installed PyTest. And then there is the Nose and Nose2 packages. It's also an automatic test framework, but the community, let's say, it's somewhat smaller than from PyTest, and therefore we will concentrate on PyTest in this video. Now let's have a look at the tests. Okay, so let's start for our Spider environment where we just worked in, and if you remember, we had here a folder called projects or pipe projects, depending how you named it at the end. And if you go to the projects folder or pipe projects folder here, we have just the LinSolver project, which we started to develop. And in order to test the functionality of the testing itself, I would like to start a new project instead. Right, and this new project will be a very simple one. This project should be a mathematical library, a mathematical module, which are containing trivial mathematical routines, which we may need, and we will implement one of those trivial mathematical routines. This is the factorial routine, right? So basically, what I will do, I will just here close the project which I had before. I'm just closing it, and then we will just create a new project. So we are saying here new project, and the project I want to put into this project or pipe project directory. If you look at the slides, I'm using pipe projects folder. Here I will use the project folder, but it doesn't make any difference. And I will call this project mymath. So basically that would be just a small mathematical routine module containing a few absolute trivial routines for didactical purposes. Okay. Now we have created this thing here, and basically it will contain two files. It will contain the file mymath.py, which will contain the routines. So here is the mymath.py, and I can already, just a good habit, start to make here a comment, a document, doc string saying contains trivial mathematical routines. Okay, and at the same time, at the temp.py I can close, and at the same time, when I have mymath.py, immediately I will create a new file, a second file, which contains the tests for that. So basically, I will just create a file. I will just call it test mymath.py, and that will be basically the file which contains tests for the mymath module, right? So basically I immediately start. Okay, and now basically let's implement the function, the factorial function. So what would be the first thing? The first thing is maybe here I can just make the framework. So basically I can say I will have a function which is called factorial, and we can just think about what it should accept. Also, of course, it should take a number from which we are calculating the factorial and return something. Return the factorial. I will just return -1 so that we know that it's an invalid value. And this is already the right point where you should document your function, because now I already decided what this function should accept as argument and what it should return. So this is the best time to write the documentation for that. So basically I will document it saying, okay, returns calculates the factorial. We will use the Google style as we discussed already. So basically the argument one is num, and then just bring the number, calculate the factorial of, and then that's the only one, and then we have to say returns. And what it returns, it returns basically the factorial of a given number, the factorial of num. Okay, we can even also write this is num factorial. Okay, good. And that basically we have everything which we need. The only thing which we are missing is the implementation. And of course the factorial itself is not very difficult to implement, but basically we will postpone this implementation because we can assume that this is something complicated, and the first thing we will write is a test to make sure that the implementation is correct. Now the big question, what kind of test should we write? And basically here we could just test whether it's for a given arbitrary small integer gives the right value. For example here for the factorial, whether factorial 5 is giving the right value, and we could make a test which tests whether if we are passing 0 as an argument I get the right value, because that's not necessarily trivial. So let's do that. So basically what do I have to do? I have to import the mymat module in the tests, of course, and then I have to write the tests. No, the test, usually the convention is that the test always starts with a prefix test and an underscore, and then you write the name of the test, and I just call it small integer factorial of small integer, or I will just write factorial small. And what should this test do? And basically this test should do nothing else, just calculate, let's say result is mymat 1 factorial. You see the factorial function has been already recognized by the editor, and I am just taking 5, and then I have to check whether the result is correct. The result should be 120, and the way how in PyTest I have to check it is I have to make a so-called assert, and the assert in the assert I'm writing a condition, and basically if this condition is fulfilled then the test is passed. If the condition is not fulfilled then the test fails. So let's say just check whether the result is equal 120. Okay, and then the second one I can say test factorial of 0, factorial 0 for example, and then I just as a result I just store mymat.factorial of 0, and I will check whether the result is equal 1, because I know that factorial of 0 should be 1. Okay, and now you see here already that something is not correct here. Here I have something which says code analyzes invalid syntax, and that means of course I have to check whether the result is equal 120, so I have to compare it, so I have to use the comparison operator, and also here not the assignment of course. And now it seems that the IDE, the developer development environment, is happy with the code as it is. Okay, now we have made the test, but of course we have to execute the test somehow, and that's the next task we have to check how to execute. And there are two ways basically you can do that. The first way is that you are going into the folder where the project is stored. So basically here I will just go into the mymat folder, and we see exactly in the mymat folder I have the test mymat and the mymat.py files. And okay, what we are do, I can just say Python 3, and then I'm just starting Python 3 and just importing the PyTest module. And if you start Python 3 with importing the PyTest module, PyTest automatically will discover what kind of test you have in your system, in your folder, and every subroutine which starts with a test and underscore will be basically interpreted as a test and will be executed and tested whether the asserts in the tests are fulfilled or not. Okay, so let's have a look at that. What happens if I start it? And yeah, it's started. We can see, okay, the test session starts, and then it was it finds we are in that project in MyMath, and it has found the test MyMath file which apparently contained tests, and apparently it contained 2 tests, and both of them were executed, so 100% was executed, and both of them are the here false, or a failure. That means the tests were, so the F stands for failure, the tests were not successful. And then we can have a look, why not? Because here I had a result, an assert, whether the result is 120, that was the first routine, and you see that basically it was substituting for result, substituting -1, and because that's what our code returns. If you remember, we just didn't implement the code, which is returning a dummy value of -1, and indeed that's not the right thing to return. So basically you see -1 is of course not equal to 120, so the assert is not fulfilled, and therefore I have an error here. And the same here. So basically it seems we have 2 tests, and both of those tests were executed, but none of them passed. So basically 2 tests failed. And that of course clearly shows us that there's something wrong with our code. The code does not fulfill our expectations, so we have to work on that. But before we continue and with the implementation, I would like to show you how you can run it from Spyder, because this is even more much more convenient. You can basically in Spyder go to run and say run unit tests. So you are selecting the test routine, test MyMath, and then you are running, you say, just to demonstrate more, you say run and run unit tests. You click on that, you have to select the test framework, which is PyTest, and this is basically what we have to deal with. And you see the Nose framework is not even available anymore in the plugin which you installed. So as I said, the support is not really clear for Nose, but PyTest works quite nicely. And then we are just running it. And now you see that here I have here the results in the right window. Here there is a unit testing tab, and we get exactly the same error messages as before. The nice thing is it's colored, and it's in our integrated development environment. You can basically here unfold all of them, and you get the same information as before. And the nice thing is you can also click on the lines, and then you get exactly the line, the affected line in Python. Or here, for example, if you double click on this definition, then you get it here. So you can think of that if you have more than 2 tests, you have several, let's say hundreds of tests, then here you can get a very quick overview which test failed, and basically click on that, and here you get the summary. Here it says up to tests failed, 0 passed, so we know that it doesn't work. So it's very, very convenient and to execute it from the Spyder environment. Okay. And that's already quite good, because that makes the possibility of having the executing tests very fast. Okay. Now what happens if we implement the feature? We can just test it, whether it works or not. So basically, instead of returning -1, we can just say, okay, what do we have to do? We just have to set up our initial value. Let's say result is 1, and then we have to just go from with n in the range from, let's say, 2 to the number +1, and then basically make sure that the result is equal result times n. Right, and then if we have the result, we can just return the result, but not the result, of course, but the returned result. So basically we didn't change the interface. The interface is the same. We didn't change the test. The tests are the same, but now basically we changed the implementation, and now we can test whether the implementation still works or not. You can just go to test MyMath and then say run and run unit tests, or you can just push Alt Shift and F11, and then basically if you do that, the tests are run again, And oh, that looks so much better, because you see here that basically 2 tests were passed, and basically both tests returned the right result. So basically no, we satisfied all the tests. Okay. Now of course here we only tested for one integer, and it would be quite nice for one number, the number 5. But of course, why should we only test for the number 5? It would be good to test for several numbers. On the other hand, it would be quite dumb just to return, just to basically just to repeat the same and the same subroutine, and just to change the number here, let's say on 2, and check whether the result is 2, and just to change the number here, let's say to 3, and check whether the result is 6. I mean, we can of course do that. And if of course we should have also changed the name, so that would be test factorial of 2, test factorial of 6, and that would be then test factorial of 5, right? And then I could just save it and try to execute it with Alt-Shift-11, and then okay, now I have much more tests, so you can see it. I will just here show you. You have now 4 tests, and all the 4 tests passed. But let's assume you want to check it just to be on the safe side for 2 or 3 more entries, and then you would have to here repeat the code and again and again. And this is not something you should do, right? So basically, we would like to have a more elegant solution for that, and this is very easy to achieve with a so-called parameterized test. That means basically we are running always the same test. The only difference is that here the number 5 and 122 and 2, 3 and 6, that those pairs change. And basically it would be good to have a loop which runs over all possible pair combination which we are just describing, and then PyTest should execute the same test, exactly the same test, but with different values. And this indeed you can achieve very easily with the so-called factory parameterized tests. And this is exactly what we will do. We will just collect into a list basically all the possible combinations which we want to check. Basically here the number as a tuples, number and result, then another tuple with number and result. And we want to convince PyTest to run over those pairs and call a function. And in this function, basically, let's call the pair factorial. We will just here basically collect the first one. This is in the variable fact, the second one in the variable result. And then we will just call mymat factorial with the number, fact, and checking whether it is the same as result. This is exactly what we would like to achieve, and here in the slides you see you can just achieve it with a so-called function marker or a decorator, so-called Python decorator. I won't tell you in detail what a decorator is for the moment. Basically, a decorator takes the function which is after that and transforms it in a different function. So basically, how it's done internally, it's not so important at the moment. This is a little bit more advanced Python programming. You can look it up if you like later more in detail, but just know for the moment just to use it here. Okay, we have before the function, the actual function, we have to make a decorator, and this decorator will make sure that this function here is embedded in another function and will be called with the right construct step by step. So let's do that. So basically what we would like know to achieve is we would have to import the PyTest module explicitly. We would have to define a variable, let's call it factorial, or a list, which will just contain the tuple of pairs. So basically, if we are calling with 0, it should give us 1. If we are calling with 1, it should give us 1. If we are calling with 2, it should give us 2. If we are calling with 3, it should give us 6. Let's say if we are calling with 4, it should give us 24. And let's take some higher value, just something which doesn't take very long. If you are calling with 8, it should be this number here, 40,320. So basically, if you are calling with 8, it should be this value of 40,320. And then basically we will just create a function. Let's just call it text factorial without any addition. And we want to make sure that PyTest will run it over this list here. So we have to decorate it with the PyTest marker, and this is called parameterize. So basically, if you look at the slides, it also shows you that you have to call the pytest.mark.parameterize here decorator, and this needs basically two arguments. The first is a string, which is the variable name. So basically, all this thing will be called in the function which follows what kind of variable name, and just let's call it just to be consistent with the slide. I will call it factorial. So basically, this is the results or a pair of an input and a factorial calculation, and it should run over the list, but not factorial, but factorials. I would like to call it factorials because it's a list of tuples. And then here I have test factorial, and the test factorial should exactly basically accept one variable, and this variable name what you accept here should be exactly the same as the one you specified here as a string. So basically it will accept a variable called factorial, which will be one of the entries from the list factorials. So basically the pytest will run over all the entries and pass the entries one by one to the test function under the name factorial. And then the only thing, I will just unpack this tuple to make it a little bit nicer. So basically I will call it num and the result, and the num is factorial. So basically the first one in the tuple is the number from which you want to calculate the factorial. The second one is the result. And then basically the only thing we want to check whether assert where the result is the same as my math factorial of the number. And with that, basically I can spare this test, and also this test, because I'm also checking explicitly on the 0. And now if I'm running the tests, you can also click here to run the tests. Then we can have a look whether I was successful or not. And you see that basically here it was run several times with several different items. So altogether it was run 6 times from 0 to 1, and basically all of them are valid. Now let's assume I'm just making a mistake here, just to demonstrate what happens there. And then with Alt-Shift F11, I'm writing the test again. And oh, you say, okay, one of the tests failed because, and here it also already tells you what was the value of the variable when the function was called, and the factorial was a tuple. The variable of the factorial here of the tuple was 8 and 4,320. And then it says exactly here, I had here an assert, and this assert was not correct because what was returned by the program was 40,320. What was expected, because was declared here, is 4,320. So indeed, you would get an error if something is not matching, and from the output of pytest, and this is very important and very nice, you can find out what was the value which was passed to that routine, right? And of course, what we have to do, we have just to correct it. So just let's write it back here, and then let's run the tests again. And then now, if you're running the tests, then all of them were executed and all of them running. So we can be sure, okay, fine, our program works as expected. And that's of course very, very important. Here I want just to show you another example. This is not we are not programming, but if you are continuing developing your LinSolver project, of course you can do something similar there. Parameterize the examples, either by storing the matrices in a tuple or a list, the matrix which goes in, so the coefficients for the linear system of equations, and then also a second element of the tuple. You could store basically the result vector and then see whether they are the same or not. The only thing is you have to keep in mind that maybe it's, especially if you're testing larger matrices, it's not that nice to write it in the code. So basically what you could do is store the input matrices, the coefficient matrix, on disk under a certain name in a certain directory, and the result also under a certain name in a certain directory. And then you could basically pass the name of the directories which contain an input file and an output file to the parameterized tests, and then in a parameterized test you could basically read in the input from the directory which is passed as test name, and read in the output from the directory which is passed as test name, and then call basically the Gaussian eliminate routine and then compare the things to each other, right? So basically, but this, here the principle would be exactly the same, with the difference that you are reading the input and the output. So basically, what goes in the argument and the expected results from disk, because especially if you want later to test for large matrices, it's definitely much better. Here in our example, it's much easier. We can just define here the values, because those are just single numbers, so it's quite trivial to do so. Okay. The other thing which I would like to show you with test is the so-called test fixture. And test fixture is something which you can use if you want to set up for every test the same environment. That means you want to, for every test, you want to exactly do the same steps at the beginning in order to initialize an environment for the testing. In our case, this is not really necessary, but we will come up also with an example. But think about, for example, if you want to test something which communicates with a database, and first you have to retrieve some kind of data or build up some kind of data structures in order to that you can execute the tests. And if the steps are always the same, then it will be a pity to repeat the code. And then you can create a so-called test fixture. And all the tests which are using that fixture will basically execute this code before they are starting. In order to demonstrate that, let's have a look in our case. We will just make tests which are checking arbitrary numbers, so basically random numbers for the factorial. And of course, then you can ask the question, how can I check random numbers? If I'm just taking a random numbers for the input, for the num, then how can I test the result? And of course, then I cannot test the result because I don't know which number has been chosen. But what I could test, for example, is whether if I take a number less than this randomly chosen number, then we know that basically there is the factorial and factorial of n and factorial n minus 1 has a very well defined relationships to each other, because factorial n is the same as n times factorial n minus 1. Also the same if I'm choosing a random number n, factorial n plus 1 is the same as factorial n times n plus 1. And that we can use for a kind of consistency testing with random numbers. Now our tests which are testing it, all of them would need the creation of a random number before they can start. And because we will have more than one tests which needs those random numbers, I would like just define a routine which does that. And in order to be simple and also to be consistent with the slide, I will just call it small rand int. So it will give us a small random integer. Why should it be small? Because we will calculate the factorial of that thing, and that should not be very big, because a factorial of a big number could take long or could cause problems if the integers become very large, and with factorial that happens very fast. So I'm just here defining that, and I will use basically the random module of NumPy in order to generate random numbers. So basically I will just import numpy.random as let's call it just random, so that we don't have to type so much, and we will just get a number, a random number, which we are just calling the random function, which gives us basically a random number between 0 and 1. And in order to calculate the factorials, I want to make sure that I get a number between, let's say, 1 and 10. Then I would just multiply, so the random integer would be just a multiplication 10 times random.random. Then basically I get a fractional number. The random.random returns me basically a floating point number between 0 and 1. I'm multiplying with 10. I am just converting it to an integer, and I will just add 1 to that to make sure that I am in the range of 1 to 10. And because it's not necessarily trivial, I can just here make a comment. So basically transform random number or transform number into the range of 1 and 10, and both ranges are included. and then I'm just returning this this random number here. Return random integer. So basically here and here you see there's a comment, and it says the local variable rand is here it says is assigned but never used, and indeed I was just writing the same here again. So basically I could just use the local variable which is just set up. It's also nicer and more compact. Okay, and then I'm returning this random integer. Okay, so basically whenever I call this function, what will happen? Whenever I call this function, I will get an integer, a random integer. We can just test it whether this works or not. So let's try to import here this test mymat. I'm just importing it and just call small rand int, whether this does what I want. And it doesn't work because of course I have to tell it this mymat dot small rand int, and no, it didn't work. Why? Because it's called test mymat dot small rand int, so it was test mymat. There we go, and I get 3, and now I'm executing again. I got 6, executing again. I got 6 again, then 10, then 8, then 7, 7, 3, 2, 2. 9, and so on. So you see that basically it's really a random number. So it does the right thing, it delivers a random number. And now I would like to write a test, and this test should use this random number, and that means I would like to have a consistency check, which basically just you can look at here at the next slide, which basically tests lower consistency, which checks whether n times factorial n minus 1 is the same as factorial of n. So basically I will just say test lower consistency, and then here how can I invoke this fixture? First I have to mark this fixture. I have to say this is PyText a fixture. So basically if you look at the slide, it's also showing here. The only thing you have to do is mark it as a PyText fixture and return something, and then basically here you can refer to this fixture by its name, small rand int, and basically that means that you will get here the small rand int in the variable small rand int, whatever the function, the fixture function small rand int basically here gives you back. And just not to have to type so much, I will just rename it the small rand into a smaller. And now I want to check the consistency. And what does it mean? I want to check that basically assert. I want to make sure that mymat dot factorial, if I take n, then it's the same, the factorial of n is the same as if I would take n times mymat dot factorial n minus 1. And the nice thing is with that test, of course, the nice thing is that basically it doesn't matter which number this small rand int is. It's important that it's 1 or above, so that factorial n minus 1 is at least 0, because we didn't specify yet what to do with negative numbers. I mean, this is something we have to we will deal with in a second. And then basically this random number can be arbitrary, and then we are just checking for consistency. And the same I will just do with the upper consistency. So basically, again, I'm just taking small rand int here, and then again I will just store it. Here I'm missing the n, small rand int. I will just store it as n in order that I can make a more compact expression here, and then I will just check whether basically here the mymat factorial n plus 1, whether that's the same as mymat dot factorial n times of course n plus 1, or I will just write here n plus 1 in the front, n plus 1 times. And again, this is a consistency check. which is basically independent. It should be always ensured independent what this more and int value indeed contains. And we can check whether that works or not. So Alt Shift Alt F11, and let's run those tests, and that looks already quite good. Let's check whether the test was run at all. I mean, that's the first thing. So if you look up here, you see that the test lower consistency and upper consistency has been run. Okay, now let's make a mistake here just to see what happens if something doesn't work. And let's run the tests again. And if you do that, we should get an error message, which we get. Very, very nice. And now the question is, what was the random value which was set up here? And you see basically that the number was 8, because here the assert is that whether this value here is 8 times whatever came out. And if you look at here the input, you also says whether here and here here was the function call of the factorial with the argument of 8. So basically here where my cursor is, you can see that the number 8 was passed. And if you run the test again, so basically the test suite again, of course it fails again, and now you see that the number which was passed was the number 2. Okay, so here what was passed is the number 2. So basically, indeed, basically every time you run the test suite, or even for every function, always separately this function, this morand in this code, and then you get always a different random number. Okay, we want just to revert the changes and then run the tests again, and then if you run the tests again, now everything is fine. So basically with that, it turns out that we have nice tests and we can test our program quite nicely. The only thing which we do not test yet, or also we didn't implement yet, is errors. And that's a big question, whether how to do that. And this is something we have to think about, because our factorial function at the moment is only able to deal with positive numbers and 0, and only with integers. So it will be very important that we are here at the beginning checking whether we are looking for whether some errors occurred. And let's say the trivial thing would be to check whether the number which is entered is smaller than 0, the factor of a negative number, or algorithm cannot deal with that. So we should do something. And actually, we would have to raise here an exception. We will learn in the next lecture what exceptions are and how they can be raised, so an error condition. But now let's make it simple. We will just return none. So basically this function returns none if the number if the number is less than 0, and we should also check if the number is an integer. So basically we will convert the number to an integer which is passed, and if it's just not the same that the number itself, then again we will just return none. It's not very useful, this returning of none, because the user won't know what's the reason for the error is, but for the moment this is how we can deal with. And here we should of course change the return, so the factorial of num, or none if num is less than 0 or is not an integer, right? So basically that we can check. So we have implemented that, but that's maybe not that good, because if we just go there and here run it, okay, let's just run the tests again, and everything is fine. We would think it's not the case at all. So let's have a look what happened here. Here basically the test factorial result was basically here failing, because the program was returning none instead of a number. So basically if you messed up something, it's quite nice that the test thing already code that. And why? Because basically we were writing the if here not correctly. We wrote if int num is equal num, then it would return none, but it's not the case. Actually it should be if it's not equal none, then it should return none, because that means that the number which was entered here is a fractional number, it's not an integer number. Now let's run the tests again and see whether we get a better result. Now everything is fine. However, What we are not testing is whether our code behaves correctly if an error knows here an error, basically an argument is passed which is not correct. And the question you have to think about, okay, how can I test for that? That's the first thing. And the second thing, why don't I know, or how can I realize that my code is not checking things correctly, right? And this leads us to the concept of the so-called Python coverage. Just before we do that, let me have just one slide inserted about how to compare when you compare in the PyTest arrays with each other, so not numbers as we did here, because here we were comparing numbers, but when you make basically your exercises with the help with the linear solver, then you will have to compare arrays with each other. And comparing arrays you can do by using these 2 or 3 very important functions in NumPy. You remember, maybe if we are making a comparison from an array, we can just do it in the interactive here in the interactive window. We will just import NumPy, and basically we say that the variable a should be the same as NumPy array, let's say 1, -2, and 3. And then basically the question is, if you want to compare it, let's say the result, the array b should be, or if you want to compare it against any array, so you want to check whether a is equal mp.array and then 1, and here I write just 2 and 3, then you will basically it will be compared element wise, so you get back an array which contains true or false for each comparison. So basically here I'm passing the same an array of the same shape, and it's done element wise. Or if you just pass a scalar, so basically if you are asking whether, let's say, a is greater than 0, then it's compared against 0, but again element wise. And now if you want to know if all elements are bigger than 0, then you can basically use the np.all function. np.all function, if a equals bigger than 0 and it's false. Why? Because the a greater 0 would return an array which contains at least one false, and all gives you true if everything is true in that. And the other one which is useful is any. You can look whether any of the entries is greater than 0, which means if it contains at least one true, the comparison contains, the array which you get from the comparison contains at least one true, and that's the same. And the third construct, which is quite nice, where you can substitute, you can just say here you can just say here a condition, let's say a smaller than 0. And then if that's the case, you can say, okay, here it should return the absolute value of a, otherwise it should return a itself. And then, for example, here, for every element which is smaller than 0, you would substitute it with the absolute value of that element, otherwise you would substitute with the original value. And if you look, you get exactly here an array where the -2 has been converted to 2. So those are the 3 structures and 3 constants which can be very useful if you have to here compare in the asserts not numbers but arrays, because at the end in the assert, when the expression is evaluated, you must have one single boolean value at the end, and with np.all and np.any you can check it quite nicely. Okay. Now let's continue and to the question, how do I know that I'm not testing everything? Because we have added some code here, but we are not testing for that new code yet. And this is basically the so-called coverage testing, or the test coverage. And this is the next topic I would like to deal with. So if you look in the slides, basically I want to make sure that all the lines in my code which are executing code are tested somehow. And basically I can get information about that what has been tested by the so-called coverage test. And that means I'm running my tests again, but using the so-called Python-free coverage program. And basically that you can do by going to the folder where you have here your project, and then you say Python-free coverage, and then you say run, and then you say source is equal to the current directory, and I want to execute Python. I want to import the PyTest module. Remember, if you import the PyTest module, it automatically looks for all the tests in the current folder based on the file name. And if you execute that, then basically you see that again the tests are here executed. 100% of the test has been executed, and here you have dot 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 dot. Every dot means a successful test, and here basically 8 items, which means 8 tests were executed. So far so good. It's not different from that what you had before. However, the nice thing is if you run the test with Python free coverage, you can now basically check whether you really tested all the codes, and that you can do with the coverage report command with a small, basically a short summary on the console. So you can say Python free coverage, that's the routine, and you have to take here the command instead of run, the command report, and then the option -m. You can just look up later what exactly -m does, but basically here it says, and this is exactly the important, it was running the code, the lines in mymat.py, and it was running 9 lines, 9 statements, and it was missing 2. So basically there are 9 statements, but it's missing 2 of them. So that means only 78% of the code has been executed. There's 22% of code lines which have never been executed during the test, and that means, okay, I am missing some code lines, and actually it says those are the code lines 14 and 16 which are missing. And if you are looking in your mymat.py, indeed this one is never tested and this one is never tested. So we never had a test which was generating those error conditions which would have led to the function returning none. And now our purpose is of course to write tests which are covering it. If you have more than 2 lines, then it's not very nice if you just get numbers here, and it's much better to get it graphically in a browser. And this is where you have basically you can do generate, instead of generating this report as we just did. You can, so here coverage report, instead of coverage report, you can just say here coverage, and then but HTML, and then you have to specify a directory where it should create the HTML file. So we will just do that. We were just saying Python's free coverage, and then we would like to have an HTML report, and basically the result should be stored in the coverage HTML directory. And then basically it's the same as the coverage report as before, but now the report is stored in this HTML in this folder, and you see it indeed created a coverage HTML folder. And then basically I will just start Firefox to have a look at the index.html in that folder. And if you start Firefox to have a look at that, then you get the same statistics as before. Okay, so the information contains nothing new, but now you can click on the file on mymat.py, and then you exactly see there were 9 statements, 7 run, 2 missing, and you see the 2 missing lines are marked by red. So you immediately see, okay, those are the 2 lines, the red marked lines which are never executed. And of course, now what we have to do is to implement something which basically covers that. So basically we have to go back to our Spider project, and we have to make sure that we are testing for the cases like we just say test and negative. And the test negative would do what? Basically it would test whether assert let's say mymat.factorial, whether if I pass, let's say -1, then I get none. And you know that you should never compare with equal with none, because none is a singleton. You should test with the is operator whether the result is none. So we are testing whether mymat.factorial would return none. And we are just making another test, let's say fractional. So we are testing for the fractional, and then we are saying assert that mymat.factorial. Let's say if I'm passing 3.2, then I should get also none. And here we see exactly here both of them would return none, and I'm just testing it. And now I'm just starting the test with Alt Shift F11, and then here First, I test whether everything is fine and whether those new tests appear at all somewhere. And that seems to be the case. If you look up here, the things, you see that the test negative and the test fractional has been also executed, and they are okay. And now we can go back here and run the tests. I will just put that in the background with BG. So I just pushed Ctrl Z to stop, suspend the project, and with BG I just put it in the background, and it's the same as I would have started it with the end at the end, so that I got back the prompt. And now basically what I'm doing is I'm just running here the coverage run in the same folder, so the tests are basically done again, and now the coverage information has been collected. And I will just here basically create the HTML report again, and then now I'm just going here to the browser and I'm just reloading the index.html file, index.html, and if I reload it, that looks much better. You see the statistic. No, it's 100%, coverage is 100%, and if you look at the file, everything is green. That means all the lines has been run. So basically I'm covering all lines in this test. Of course, 100% test coverage doesn't mean that doesn't mean that your code has been tested for every possible errors, but at least you know that every line has been tested at least one. And with that, I would like to finish the testing session, and in the next session we would have a look whether we know that our code works formally correctly, so the algorithm does what it should. We would have a test for that, whether our code, as we have written that, is nice enough to read or not. Thanks a lot for your attention so far, and see you in the next session. Bye.